Hi, this is Dr. Mark Barkey at the University of Alabama. This is a video for the Class AEM 649 fatigue analysis. And what I want to do in this video is to kind of give an overview of our project that we're going to have for our class. And the project is mostly for everybody going to be the same. There's going to be a little bit of individualization later. But what the project is for a fatigue calculator. So you're going to take a time history of either load or strain or stress or something and come up with the fatigue damage for that time history, and then change some things and make some fatigue calculation evaluations. And so in this video I want to get a kind of an overview of this entire process, and then we're going to make other videos later in which I go into detail in the specific steps. So the intent is we'll study each of these sections or steps to this project in detail, but this video may be something that you might refer to a couple times during the semester to kind of make sure that you understand where we're headed with this and what the kind of the big picture is. So for our project, we have some materials on our box folder that we have here, and you can see there's this folder called Project Materials. I've downloaded that and have that available to look at on my computer. And then also something in here called Fortran and Utilities. And in this particular folder is Fortran. Here's an example Fortran program and something called Crimson Editor. Crimson Editor is, in my opinion, a very nice text editor for working with text files. Has the added benefit that it was actually developed at the University of Alabama. And in the Fortran folder is Fortran that you can download and install on a Windows type PC. Now, you're going to have to use a programming language. Doesn't matter to me which programming language you use. In the past, some people have used C, C++, Fortran, MATLAB, Python, anything that you want. Eventually, you're going to have to take the data and make plots with it. Fortran is really good with generating numbers in text files, but I'll show you how to take those files and write them in a format that can be easily read by Excel, and then you can make the plots in Excel. Fortran is what I know personally. Fortran is what I can help you with the syntax and getting the program compiled and so forth. So I'll make a note of this. I can help with Fortran, but not other languages. And I would say not the specifics of other languages. Now the general logic flow, we'll talk about that in our lectures. And if you can translate the equations that we have and the algorithms that we're developing into your programming language of choice, then that's great. Again, when we get down to very specific details about how to get this thing to work, then I'll probably resort back to my knowledge of Fortran. And I'll mention this here, that Fortran, it's an older language. There are still commercial codes for numerical analysis that are written in Fortran, and then they also interface with newer codes like Python and things like that. The syntax is very specific in Fortran. You have to have things in certain places, and that goes back historically to what's involved in Fortran and how it was initially used back when there were things like punch cards and things like that. So there are some specific quirks, and it is not considered what's called now an object-oriented language. Object-oriented languages tend to be like the newer things like Python and so forth. And they have certain constructs and all these things that are kind of abstractions to me. The thing I really like about Fortran is very concrete. You do it right, you get the answer, and you're done. Maybe it's not as flexible and wildly able to process different formats of values like things like Python might be. But for our purposes here, Fortran is certainly good enough, and it's still useful in industry in different places today when you need to focus on speed, low overhead, and getting numbers that you can do something else with later. All right, well, that's enough of my plug for Fortran. Either you're convinced that you might want to use it, or if you've used it in the past, or you've already decided you're going to use some other code. Either way, like I said, is fine. But this is something you should think about at this point in the class, kind of early on. What are you familiar with? If you don't know anything, then I'd suggest Fortran or MATLAB if you have access to MATLAB, and as a student you should here at the university. But make your decision now what kind of programming language to use. Oops. So let's just make a note. Decide what to use now. Or how about soon? All right, so again, for an overview of our fatigue project, at the end of the semester, we're going to have something that will take a time history and calculate fatigue. Let me clear off this page, and we'll kind of draw some diagrams here. All right, so in order to have fatigue, we need to have variable or changing stress or strain or load, or something that changes with time. So you'll often see me make plots with time on this axis, and just for the sake of having something, let's say that we have a place on our component where we're measuring strain, and we have this time history, and it does something like that. Now on this time history, typical digitization process, something to turn in this strain signal, which is a mechanical quantity that's happening on maybe the surface of a component, into a digital time history. We have to use a transducer of some sort, which would be something like a strain gauge. We take that strain gauge and we would run it through a computer system to collect that data at some certain frequency of data collection. So we may have a start to our data, and it may have just tons of points in it. Modern data acquisition systems can take data at fairly high frequencies, and so we can end up with just tons and tons of data. Typically this data would either be a text file, those are usually the easiest to work with, but it could be a binary file, where we've stored all these different values. Okay, so you'll take a time history of data, and for our purposes, it's going to have a constant digitization rate, or data acquisition rate. But it doesn't have to be. Our time histories will be a constant data acquisition rate, but you can have a variable data acquisition rate. The important thing for us initially is going to be to determine the peaks and the valleys of the time history. All right, so I'll draw another kind of a simple waveform. This would be a cosine wave, And often in testing machines, for reasons we'll talk about in class, we do testing with sine waves for fatigue testing. And so again, we may have a whole lot of data points along the sine wave. And there's actually recommendations if you know the frequency. But again, for our purposes, when we're going to talk mainly about metal fatigue, our purposes, we're mainly interested in the peaks and in the valleys. So if we look at this particular picture, we can identify this as a peak, and maybe this point is the valley, and we have this one here. So what we're going to end up doing as one of our first steps is to create a algorithm that will determine if we have picked the peaks and the valleys of the time history. Those are the things that are going to be important for us. So we might say this one and this one and this one might be the ones we would want to keep. And we'll go through and we'll talk about this algorithm in a separate video. The other thing that we'll need to do is, for purposes that'll make more sense later, we want to rearrange the time history so that it starts and ends with the highest peak. So in the bottom figure with the cosine wave, this already does start and end with the highest peak if these are the same values. If we look at this other time history, let's see if I can use a different color. It looks like this is the highest peak right here. And so really what we want to do is we want to rearrange this time history. It starts at this point. It goes here, it goes here, it goes down here. And then it continues on and goes here, and here, and here, and here, and here, and so forth. So in a way, we're kind of cutting that time history and pasting it so that we've cut off everything to the right and pasted it to the left. Maybe I can even show that here in this picture. So I'm just making a duplicate of this, and then I'm going to go here and I'm going to a little bit off there. Let's see if I can do that. Okay, so we have that part of the time history, and now I'm just going to stick it over here. And then we're getting rid of this part. And so it started here at 0 and we're down here, so we still need to connect this. But now see, this point isn't a peak anymore, so what we really want is we see if I can maybe circle these. We want like this one, this one, this one, this one down at the bottom, and skip this one, and we want to keep this one. This has something to do with we're getting ourselves set up to do a standard rainflow cycle counting algorithm for determining hysteresis loop cycles. Now, if you haven't taken this class yet, you don't know what all those terms mean, but kind of bear with me and we'll learn about all these things as the class goes on. Okay, so with this time history then, we want to do this cycle counting. Rainflow is kind of an interesting name. We'll learn about where that comes from. But it is a way to identify cycles in a time history. And we think of these as the individual damaging event. So for example, if we were to do this cosine wave over and over again, we would have peak to valley, back up to peak, and back to valley, and so forth. And this is called a hysteresis loop when we plot on stress and strain axes. And we can do the same thing for these variable amplitude loading cases. Now before I get too far, let me look in our folder here. We're going to go into project materials, and I'm going to open up this PDF that says the project steps. I'll zoom in on this a little bit so you can see it. So step 1, download the data sets, plot the raw data, select the programming language, have your program remove duplicate data points and rearrange the data to start and end with the largest peak. Implement an algorithm to pick peaks and valleys. Turn in a written report and send your information to me. Alright, so if we go back into the folder, here's the project materials. Inside the strain folder are 2 time histories of data. There's a pothole and there's a rough road time history, and these are in microstrain units. Now, as we go through here, you'll be able to find the peak. This is the pothole. You can plot this in Excel. Maybe we can do that here real quick for one of these. And let's see, we're going to open, we'll browse, we'll get into my class area, and then spring 21. We'll select the text files, or let's see what we can do here. And we'll open up the pothole. We're going to import with the limited width. We only have one column in here. And so we can go next and finish. So we have all that data. Let's see if we can make a plot. Insert maybe this one, a 2D line plot with data points so we can see what's going on. We might change this if we need to. Okay, so this looks okay. So again, there's a lot of data. Looks like we have about 7,700 data points. And so we see here's the peak. It starts off near 0 and it bounces around a little bit as if the car's going over a pothole, and it comes back down. So this is the kind of data that's often dealt with. Let's see if we can change the scale on this. Format axis. It's not format that I want. Well, we want to change the maximum values. Let's do this. We'll look at a couple hundred data points so we can see what's going on here. Now, computer data acquisition systems bin your data set. So it takes voltages and converts it into a number, and sometimes that number is in one level, one zone, sometimes it's in another zone, sometimes it repeats and stays in the same zone. So like here's a bunch of instances where we have the same number. So it looks like the value is 111 microstrain a few times. We do not want to have duplicate data points in our time history. So we're going to need to filter those out. So this is this, have your program move duplicate data points and rearrange the start and end of the largest peak. So again, maybe we'll get into a little bit more detail than we need to at this point, but let's add this and remove duplicate points. So we've done that, and we're going to use what's called the Ramberg-Osgood equation. We use the cyclic version of that in order to determine the size of the hysteresis loop. So if we're given strain, we'll be able to calculate stress, and we can even go back and calculate all the points that would, in theory, be along this curve for a particular material when we know the parameters for the material. The uniaxial version of the Ramberg-Osgood equation looks like this. Epsilon is equal to sigma over E, the modulus of elasticity, plus sigma over K to the 1 over n power. So the cyclic version is a little bit different. We would have delta epsilon over 2 is equal to delta sigma over 2 divided by E plus delta sigma over what we call K prime to the 1 over n prime power. And so if we know a delta epsilon, we can go back and we can find a delta sigma. Okay. Now, we do need some material properties, so part of your project will be finding K prime and N prime for use in this equation. Let's go back to our project steps. So project step 2 is to determine the cyclic properties for a particular steel. I'm going to give you the data in hysteresis loop form. We're going to calculate the constants, use something called Massing's hypothesis. And we're also going to determine what were called strain life fatigue constants for MS 6000 sheet steel. Okay, so we'll talk about the strain life theory of fatigue and something called a damage parameter. And that also involves some other material constants. All right, so after we identify a cycle, we will end up with the strain range for the cycle, delta epsilon, and then the strain amplitude, which is delta epsilon over 2. And that's equal to some material constants, sigma f prime over E. E is the familiar modulus of elasticity, times 2nf to the B. 2nf is something called the number of reversals, and nf is the number of cycles. Then we'll have plus epsilon f prime, another material constant, 2nf to the C. So we have 1, 2, 3, 4 new material constants plus our modulus of elasticity E. But again, you will use some sort of technique to solve for the number of reversals so that you can find the corresponding, given the corresponding strain amplitude for an identified cycle. So we may have big cycles and small cycles. We may use other damage parameters other than the strain life equation. We'll talk about those in class. That maybe depend on the mean strain or the mean stress. And we can see how that might influence our fatigue calculation. We'll talk about those as we go along as well. Once we have the amount of cycles for a particular hysteresis loop, we will accumulate damage. And we're going to say that the damage per cycle is equal to the inverse of the number of cycles that formula comes up with. So if we say that the damage per cycle is 1 over 100, then if we reach 100 cycles, then the part is broken. And by broken, I mean all of its fatigue life is consumed. So we may have big cycles and small cycles. We add the damages up, This is the easy part. We can do linear damage accumulation, which is known as Miner's rule. So the total damage is equal to the summation of each individual damage, which is equal to the summation of 1 over the number of cycles predicted or calculated for each hysteresis loop that we've identified. And then we can find the fatigue life of a particular time history that is repetitive. So if we go back and look at our pothole history, what we're going to be eventually able to say is for these particular material properties, this vehicle will last 1,000 potholes just like that, or 10,000 potholes just like that, or whatever the number is. We'll be able to calculate what we think that component can sustain before it has cracked and is meeting whatever we define as our definition of failure. All right, so let me save this file. Let's see, kind of save it under a different name. Nope, didn't like that one either. Right. And so that's kind of the overview of the project. So I'm going to kind of generically call it peak picking of time history. We're going to have determination of material constants. We're going to have cycle identification. And rain flow cycle counting. We're going to have damage determination, and accumulation. And then at the end, I want you to do something that is, in addition to these steps, I want you to add something to your code to give it some additional functionality. And that may be something like trying a different damage parameter, or something similar to that. Just something that goes a little bit above and beyond the basic steps that we have in our fatigue calculator. So let me go back to our PDF document. We talked about determining our material properties in step 2, and then in step 3 we have solving the Ramberg-Osgood equation and programming the strain life equations using a Newton-Raphson iteration technique. Now in MATLAB you can get away with probably using the solver. I want you to go ahead and program in a Newton-Raphson technique. We will talk about that in class, how to do that. And then the step 4 is to implement the rain flow cycle counting and damage accumulation. Step 5 is to add some additional feature in class and prepare your final report as if you're summarizing a theory manual and a user manual for your fatigue analysis software. Now, of all of these steps, the one that gives everybody the most trouble after they get started is the rain flow cycle counting. Alright, so peak picking, you can do that in an afternoon. Determination of material constants, you can do that in an hour. Damage accumulation, you can do that in about 5 minutes. Added functionality, once you have everything else, that isn't going to take very long. But this one right here, rain flow cycle counting, if you're brand new to that concept in programming, if you're not used to programming and thinking about things in a very stepwise fashion, Rainflow cycle counting can take you a week, 2 weeks, or a month in order for you to figure out. So this is the big step in this process, the rainflow cycle counting. So when we get to this part, pay very close attention and get an early start on rainflow cycle counting. All right, so this is again kind of an overview of our fatigue project for this class, and we'll get into the nitty-gritty details of peak picking in the next lecture in this series. We'll talk about all the other steps as well in detail. But I want you to see where we're headed, and then of course if you get a chance, I'd encourage you to work ahead, and that way you can bank a little bit of time for the rainflow cycle counting part.